This is the Utilizing SnowLevel to create Precipitation type module for ForecastBuilder. I'm David Church, and the Science and Operations Officer in Salt Lake City, Utah, and I'll guide you through this a bit longer module on creating winter precipitation types using the SnowLevel method for SnowLevel offices. So what is SnowLevel? SnowLevel is defined as the elevation above sea level that a snowflake begins to melt as it descends to the surface. In our gridded world, this is calculated as the height of the half-degree Celsius wet bulb temperature in the atmosphere, and is also the definition used by the National Blend of Models. The advantage to using the wet bulb temperature is that atmospheric temperature, moisture, and evaporative cooling effects are already accounted for, which provides a better estimate on when a falling snowflake will start to transition to liquid. For reference, the half-degree Celsius wet bulb temperature is about 300 feet below the wet bulb zero surface, which allows time for the liquid to start to develop as a snowflake falls. For SnowLevel offices, this is populated as a foundational grid in ForecastBuilder using the National Blend of Models. To better visualize how SnowLevel works, let's visualize a snowflake's journey through the melting process as it is defined by SnowLevel. As the hydrometeor falls past the wet bulb zero temperature, it will remain snow until reaching the level of the half-degree Celsius wet bulb temperature, or the snow level. Once it falls below the snow level, and for 800 feet below that, it is considered to be a rain and snow mix. Once the hydrometeor falls more than 800 feet below the snow level, it will be considered to have completed the melting process and all rain at that point. In order to ensure consistency across the forecast database, ForecastBuilder has several quality control checks and guardrails on this snow level calculation. The first are a set of sanity checks, to make sure that no snow will get into the forecast if temperatures do not support it. One is at a wet bulb temperature of 2.5 degrees Celsius, and the second at an ambient air temperature of 55 degrees Fahrenheit. These values were chosen to be liberal enough to support situations where snow could fall at temperatures much above freezing in dry climates. Finally, if the surface temperature is below freezing, the temperature may override snow level to dictate that precipitation must be all snow. However, if the desired outcome is not snow, but instead freezing rain or drizzle, this can be dealt with by using the prob-ice present grid, which will be discussed more in a bit. Finally, the last QC check is on reducing surface snow accumulations above wet bulb temperatures of about 0.8 Celsius up to 2.5 Celsius. With no snow accumulations allowed above 2.5 degrees Celsius. This linear phase out of snow accumulations allows for a more natural reduction in snow totals and minimizes sharp edges or gradients in snow totals over short distances. In order to create freezing drizzle or freezing rain, the prob-ice present grid is used to remove ice from the cloud, which will allow ForecastBuilder weather step to convert this weather type to freezing rain or drizzle instead of snow. In order to get these frozen precipitation types into the forecast, these conditions must be met. Having a pop above 15% with a surface temperature below freezing, and then lowering the prob-ice present grid values to at least below 50% to ensure more ice than rain or snow in the forecast. At values below 20%, ForecastBuilder will give an output of predominant freezing rain or drizzle. And then finally, in order to differentiate between freezing rain or drizzle, this is accomplished in the weather step, which can be run over smaller edit areas or time ranges as the forecaster desires. So how can ForecastBuilder be used to effectively manage snow level and the various temperature and wet bulb temperature consistency checks to result in the forecaster desired weather types? All of this work is accomplished in the Analyze Adjust step using the tools under the snow level and snow amount boxes. The first important tool to check consistency and identify potential conflicts is the Check Wet Bulb Temperature and Snow Level Consistency button. This will result in color-coded grids showing you where potential problems exist. Pink-colored grids are locations that have temperature which is too cold for snow, but the snow level will only allow rain in the forecast. This may imply freezing rain, but if that is not the desired weather type, it may be okay to not address those inconsistencies. The white-colored grids have areas where the snow level is low enough for at least a mix of snow in the forecast, but the wet bulb temperature is too warm to allow snow in the forecast. In my experience, these have been the bigger issues for forecasters to address, as the forecaster is typically expecting at least a mix of snow in the forecast given their snow levels. However, ForecastBuilder will not allow that until this inconsistency is fixed. But don't despair at these inconsistency checks, as ForecastBuilder also has the solutions to help address these issues and get you to the desired weather type. The two main tools to help address consistency problems are change temps to match snow level, which will force temperatures up or down to match the snow level. In my experience, this is the tool that is most often used to address consistency problems, as forecasters are happy with their snow levels and will want to bring the temperatures into alignment in order to achieve their desired weather type. The other option is to change the snow level to match temperatures, which will force the snow level up or down to match the temperature in your forecast. This tool will either set the snow level to the surface elevation where the wet bulb 2.5 degrees or less, or use a 6 degrees Celsius lapse rate of forecast temperature to raise snow level. In my experience, this tool is used far less, however, would be useful in situations where the forecaster likes their hourly temperature curve and wants the snow levels to better match that data set. Now, all of that background is well and great, but let's look at an example of how this might be used in reality to achieve the desired weather types and snow accumulations. For this example, we are going to concentrate on the heavily populated Wasatch Front corridor here in Utah. This includes Ogden, Salt Lake City, and Provo, and the heavily trafficked Interstate 15 corridor. Here our forecaster has lowered the snow level along the Wasatch Front with the desire to introduce a rain-snow mix into the weather grids to better align with our forecast messaging. However, when they ran the Weather Preview snow level tool at the Analyze Adjust step in ForecastBuilder, they found that the output weather type does not match their expectation of a wintry mix, and instead identifies the weather type as predominantly rain. This could be a number of reasons for this, so let's diagnose the problem. By running the Check Wet Bulb and Snow Level Consistency tool, we see a number of snow level and temperature grids highlighted in white, which points to our snow level being low enough for snow, but the wet bulb temperature being too warm for snow to be allowed into the forecast. We can further drill into this data by viewing the 1 snow level AGL grid. This temporary grid is a diagnostic tool for forecasters to visualize the expected weather type based only on snow level. At the right you see 3 color shadings. One is blue where the snow level is at or below the ground level, implying snow. Pink is where the snow level is above ground but within 800 feet of the surface, implying a rain-snow mix. And last, green is where the snow level is more than 800 feet above the ground, which implies rain. In this case, our forecaster did in fact lower the snow level along the Wasatch Front to within 800 feet of the surface, which should imply a rain-snow mix. So something else is afoot. To further confirm that the wet bulb temperature is the issue here, we can either look at the 2 max surface wet bulb temperature in F grid and try to compare and contrast manually with the 1 snow level AGL grid. However, the easier way to visualize the discrepancy is to use the 4 snow level implies snow but TW above 36 grid. This does the comparison for us. Values of 1, shaded in red on the right here, show that the wet bulb temperature is too warm to allow snow into the forecast despite the fact that the snow level is supporting it, thus the inconsistency. Up until now, these tools and grids have helped us identify the discrepancies, but how do we actually fix them? As our forecaster wants to introduce a rain-snow mix into the forecast here, the desired tool to run is the Change T to Match Snow Level tool. This will go in and adjust our temperatures and RH such that the calculated wet bulb temperature is within compliance for snow, in other words less than 2.5 degrees Celsius. As you can see it right, this has forced the surface temperature down to 36 Fahrenheit across much of the Wasatch Front. This change likely makes physical sense in the situation where precipitation intensity is driving precipitation type to stay snow thanks to dynamical cooling, a common thing that forecasters may need to manually adjust snow levels to represent. At this point, rerunning the consistency checks will quickly show our inconsistencies have been remedied by running the tool on the previous slide. The lack of grids in the 3 snow level implies rain but TW below 32 and 4 snow level implies snow but TW above 36 shows that there's no areas being identified where the snow level and wet bulb temperatures are out of compliance with each other. To further reassure ourselves that the problem has been remedied, if we rerun the Weather Preview Snow Level tool, we see that our weather grids are now expected to contain a rain, snow, or wintry mix along the Wasatch Front. It is extremely important that we use the Weather Preview at the Analyze Adjust step and ensure that we are getting the desired weather types at this point. It is much easier to fix any problems through changes in snow level, temperatures, etc. at this point in the forecast process. If you take the time now to ensure your weather preview gives you the desired weather types at this step, it'll be smooth sailing when you get to the actual weather grid generation later on in ForecastBuilder. Another item to make sure to QC at this Analyze Adjust step is your snow amounts. Similar to weather type, getting these correct in this step will ensure that the rest of the ForecastBuilder goes much more smoothly for you. Here we're going to use the Snow Amount Preview Snow Level button to generate this preview seeing it right. ForecastBuilder will allow us to see where snow amounts will be reduced because the wet bulb temperature is above 33.5 Fahrenheit or about 0.8 Celsius. Remember, this is where we will start to see a linear decrease in snow amounts up to 35.5 Fahrenheit, at which no more snow will be allowed to accumulate. The grids which have this reduction occurring will be highlighted in white, as we see on the right here. And to quickly see where within our forecast grids this reduction will be applied, view the number 2, snow accumulation will be reduced because TW above 33.5 Fahrenheit grid. The pixel shown at right will have a reduction applied to the snow amount. Now let's say for this example that we're expecting heavy snowfall rates during this time period and we don't want to see these areas reduced. In order to preserve the full snow accumulation at those pixels identified in the previous slide, we can run the lower T to ensure no snow amount reduced tool. This will lower the temperature and RH of our forecast such that the calculated wet bulb temperature is less than 33.5 Fahrenheit, which will allow our full amount of snow accumulation. While somewhat hard to see, the surface temperatures were lowered to around 33 Fahrenheit for the areas that were highlighted in red on the last slide. Rerunning the Snow Amount Preview Snow Level tool now will update the snow amounts with our new lowered wet bulb temperatures in the forecast. We can see when I step from the previous preview to the new preview now that the expansive higher snow amounts increased in the mid-elevations where temperatures were previously more borderline for snow accumulations. So finally, to summarize, if we just want to get snow to show up in the forecast, then we need to get the snow level within 800 feet of the surface. But that's not sufficient on its own. We have to make sure that we clear the hurdle of ensuring that the wet bulb temperature is below 2.5 degrees Celsius and the air temperature is below 55 Fahrenheit. Now fortunately, ForecastBuilder has the tools that we just reviewed in order to help you make sure that those consistency checks are met and that you can get snow into the grids when you intend to have them there. Now, in order to get snow to accumulate in the forecast, the wet bulb temperature has to be less than 35.5 Fahrenheit. However, you will only see 100% of the total possible snow accumulation of your snow ratio times your QPF at wet bulb temperatures below 33.5 Fahrenheit. Between that wet bulb temperature of 33.5 Fahrenheit and the hard cutoff of no snow accumulation at 35.5 Fahrenheit, a linear reduction of snow accumulation is applied to the total possible accumulation. This helps to prevent a hard cutoff and pixelation of snow accumulations, particularly in complex terrain situations. Finally, to get freezing rain or freezing drizzle in the forecast when you have pops of 15% or higher and temperatures below freezing, the main hurdle to accomplishing this is using the Prob Ice Present Grid. By creating a Prob Ice Present Grid and lowering the values to 50% or lower, you will start to introduce predominantly freezing rain or freezing drizzle, which can then be chosen from at the weather step GUI. Finally, if you are expecting impactful icing, remember to have a QPF above 0.01, which will cause ForecastBuilder to populate ice grids. So finally, to summarize using SnowLevel for weather types, the main benefits are having one main grid that drives your weather types, which is easy to collaborate between neighbors and also very easy to edit in complex terrain. The main drawback is that SnowLevel is currently a deterministic grid, and the only way to express uncertainty in p-type is by forcing the snow level to within 800 feet of the surface so that mixed precipitation is depicted. When other precipitation types besides rain and snow are necessary, additional tools or steps have to be completed in order to introduce freezing rain or drizzle into the forecast. This concludes the module on using SnowLevel to create precipitation type in ForecastBuilder. If you have any questions or feedback, please see the resources on the VLab page seen here or email us on the ForecastBuilder team.